We've already talked about energy once in this class and actually talked about the law of conservation of energy, and we did some calculations with energy. This is more of energy with reaction specifically, and to be very honest with you, what we are studying in this topic is literally like a raindrop in a river. I mean, it's minor compared to what you could study with energy and reaction. So we are very, very little bit of touching on the surface of energy and reactions. But what we're going to talk about is going to be, I think, interesting for you, and it's going to put a little bit of medical field information in your hands, which I think you'll find interesting, most of you. So if we look at this, the top part, before we even talk about energy and reactions, I need to review what are the units for energy. Joules was one. Calories. And then you could also say kilojoules and joules, calories, big C calories, little c calories, remember that? So those are all units that we talked about for energy. You could also say that energy is the same as heat in saying it. In other words, if I say energy or if I say heat, they basically mean the same thing. So anytime I say energy or heat, I'm pretty much saying the same thing. So for instance, if we look at the endothermic reaction, it says that heat is absorbed. Could I also say energy is absorbed? Yes, so energy is absorbed or heat is absorbed. Now, as far as the change in heat or the delta H is positive, we're not going to calculate the change in heat. So if you're writing on this page, you actually could just take out that statement on both of these. You could take out the delta H is positive. You could take out the delta H is negative, because we're not going to be doing anything with those. But what we are going to be dealing with is the fact that the products are higher in energy than the reactants. The products are higher in energy than the reactants. This statement, if you really think about it, has some kind of profound impacts and some thoughts that go along with it. The products in an endothermic reaction are higher in energy than the reactants. An endothermic reaction requires what as a reactant? What does it require? What is it saying when it says that endothermic reaction, what do you need? It says it, first statement, heat is absorbed. In other words, it's reactants plus what? Heat. Reactants plus heat. So we could say an example of this might be A plus B plus energy. And remember, those units could be, I'm going to write it up here. What are my energy units? You've already told me this. What are my energy units? Joules or kilojoules, calories or big C calories. So drawing kind of an arrow to show you what I'm dealing with here. A plus B plus energy, this is an endothermic reaction, will produce products or product. Meaning the product has more energy than A and B combined. Do you see that? Where in your world do you have to add energy to make something? Think simple. I bet you all did this within the last week or two. Or you have at least experienced the fact that somebody else did this. Say it. Cooking. Think about that for a minute. When you And let's go back to those brownies. I actually made brownies yesterday. We talk about brownies in here, and I made brownies yesterday. So let's take that brownie mix. By the way, if you all wonder why you saw me in a bandana the day of the test, the reason is because of this. This drives me batty. And so I'm to the point, I'm about ready in the afternoon because I go home and I go out to the field to check on the animals, and then I come back and this is what I see. So I'm going to probably start bringing the bandana. So if you see me in the bandana, you know why I have it. There's just a point. Now some days I actually get so hot I have to like redo everything again, but today I didn't do that, but I really wish I had the bandana today because the sunglasses may have to go back on the head because it's driving me batty. So I'll try not to let it be a distraction. But anyway, let's go back to this. Let's talk about the brownies. What do you have to do? If I mix up the brownies, I made a double batch. So I made a 9 by 13 pan, and I've got this down now, so I know how to make brownies. I had 2 bags of the mix. It took a cup of oil, 4 eggs, a half of a cup of water. Mixed it all together, put it in the pan. What did I have to do? Had to put it in the oven, didn't I? Now, if I had just left it there on the counter, it probably would have gotten eaten anyway. But it goes in the oven, right? What had to be added? Heat. Now, let's open our eyes for a little bit. Tell me if what this is saying is true, then why we eat brownies because they taste good, but what do brownies give us? Okay, now keep going, keep thinking. Tell me what your thought is. Have you got some profound like, ooh, that, where are you going with this? Somebody thinking it? Somebody going from, wait a minute, if they're cooked versus uncooked.
There's more energy when they're cooked.
Say it again.
There's more energy when they're cooked. So the product has more energy than the reactant.
Now, does anybody, I like raw batter. What are we saying? What are we saying? The uncooked batter has less energy than the cooked batter.
Does it mean less calories?
That's what that means. That's what that means.
You could say you're on a diet.
She's got a new diet. It's eating cold raw batter. So the frozen cookie dough is even better, right? Now, what's going on though? Why? Is cooking brownies or cookies it's a chemical reaction? Is it an endothermic reaction? Does it take energy to make that reaction? Yes, it will not work if you just set that pan on the counter. It's not going to cook. You have to give it energy. Now then, how could you test it? It would be a little hard to test, but you could test it in the following manner. Now, it probably wouldn't be the absolute best test, but you could try this and see if it worked. And some of you, if you had a high school chemistry class, you may have done something like this. Have you ever used any type of food to heat up water in a can? Have any of you ever done an experiment like that? You can actually, for instance, if you want to see the calories in a nut, if you want to calculate the number of calories in a nut, you actually can burn a nut and use that energy from the burning of the nut to heat water in a can. In other words, like a Coke can, if you put a certain amount of water in the Coke can, you check the temperature before, you know how much water is in it, then you can do the calculations, and I could show you how to do the calculation. So what you could do, you could dry out your mixed together brownie batter so that it would burn. I don't think it would burn wet. I think you would have to let it dry. You'd have to let it air dry, and so then it would be, the sugar would burn. So then you should be able to catch it on fire, which would take a little energy to start it, but once you got that, catch it on fire, see the change in the temperature of the water, and you could calculate the calories given off. Then you could do the same thing by burning a cooked brownie of the same quantity. Does that make sense? And you could see then which one had the most energy. You could do the calculation. Now, is this something I've done? No, I haven't done it. But based on what the facts are telling us, it should. Now, is there enough difference? I don't know. I don't know how much difference there is. But based on what we're reading, cooked brownie mix, cooked cookies, cooked bread, cooked any batter cooked has more calories than uncooked. Okay? Which means then, again, I'm just wanting to confirm this, reactant A plus reactant B plus, now instead of saying energy, what could this say? A number, it could say heat, or it could say a number with one of those units, correct? Yields the product. If it's an exothermic reaction, then heat is released. If it's an exothermic, heat is given off. And in that case, the product or products are lower in energy than the reactants because they are giving off energy as a product. And so this would be an example of that. A plus B yields product or products plus energy. In other words, energy is given off. Tell me a reaction where there's always energy given off. And this is a broad term for reaction, but what kind of reactions is energy always given off? Burning. Anything that's burned is giving off energy. Anything that's burned is giving off energy. Okay? All right, so are you guys exothermic or endothermic? Chemical reactions going on in your body. What do you think? You're exothermic. You're exothermic. Have you ever been in a situation where you're kind of in a small room with you, and maybe you're the first person in the, like a small conference room, and you might have been the first person to go in the room, and then a little bit later people start coming in and it ends up being like 10 people and you're in there for an hour? By the end of the meeting, how do you feel? A lot warmer, don't you? Why? Because all those people are exothermic reactions giving off heat. And so that's an example of that because of the giving off heat. All right, the energy of activation, that term simply means the minimum amount of energy needed for a reaction to proceed. The minimum amount of energy needed for a reaction to proceed. The minimum amount of energy needed for a reaction to proceed. Let's go back to those brownies. The house yesterday might have been around 77 degrees Fahrenheit. Was that the activation energy for the brownie mix? If it was, what would I have started to see happening on the counter? They would have been cooking, wouldn't they have? So did I reach the activation energy at 77 degrees Fahrenheit? No. Now, is the activation energy 325 degrees Fahrenheit? Probably not. It's probably lower than that. But they have developed with lots of experiments the time factor. I mean, brownies really do take a long time to cook, honestly, when you think about it. Overall, they take a long time compared to a lot of things. And so they've figured out the time factor to still keep them the consistency they want, cook everything, reach the energy barrier, which is the activation energy, but still not get overcooked, too dry, etc. So that's where we're getting at. But the point is that dough or batter, when you put it on the counter, that temperature in the house is not. enough energy to cause it to go. That's the activation energy. Reaction rates, when we say the term reaction rates, what we are basically referring to is how fast a reaction occurs. How fast a reaction occurs. And we are going to touch on two factors that affect reaction rates. We're only touching on two. There are tons of things that affect reaction rates. We're touching on two. The first one is the concentration of the reactants. If you increase the concentration of the reactants, then what you're doing is you're increasing the number of collisions, which then cause the reaction rate to increase. Not to treat a sensitive subject insensitively, but I'm going to approach this with something that is, for some of you, has no meaning now, but eventually might, and for others of you might have meaning right now. When conception occurs, you have typically one egg that's released per month, but is it bombarded with one sperm? No. In fact, the quantity of sperm is like 13 is a low minimum. 13 million is a low minimum. It's more like 20 million. Now, think about that for a minute. Does that mean that every time 20 million sperm get released, do they reach the egg? No. Why does it take that many? You would think you have that number. That's a huge increase the concentration of reactants. That should increase the collisions, right? But what's the problem? Say it again? They die, and basically they're going uphill both ways. I mean, that they have a hard journey. They have a hard journey. Now, what is the first step in infertility? Anybody know what the first step in infertility is? I'm not expecting you to know this, unless perhaps you were the results of infertility treatments, which some of you very easily could have been, and maybe your parents told you this. They're going to check sperm count will be 1, and if sperm count is low, then that's going to be obviously an indicator of something's going on. What do they typically do as a first resort, though? They don't do in vitro fertilization as a first resort. What do? Which is based on this same thing right here. Say that again? They may do the artificial insemination, but with artificial insemination, they also do something else. Fertility drugs for the who? The woman. Now, how do fertility drugs in women work? They increase the number of eggs released. That's how so many times you hear the stories, not as much recently, but in the past, you would hear the results of the what's the best word? Not the best controlled drug use. That's not the best way to put it. But what you would have happen is you would have folks taking the female taking the infertility drugs, and they either responded in a much better way than they had expected them to respond, and that caused them to super ovulate. And these are terms that are actually used. So it would cause them to super ovulate, so then they would have not 1 egg, but maybe as many as 8 eggs or more. So does that increase the concentration of reactants? Yes. Then they may go with the artificial insemination, which helps eliminate part of the barrier. Even then, if that doesn't work, then they may go to normal in vitro fertilization, which is where they get out of the human body and in a petri dish, they call them test tube babies, but it's actually done in a petri dish. In a petri dish, you will put the sperm in, put the eggs in, and basically let them do their thing. And then there's other avenues to go past that if that doesn't work. But that is a real life medical scenario that is going on, and it fits this. I mean, to me, it is one of the better examples in a real world medical aspect that is exactly this. Increase the concentration of reactants, you're going to increase the rate of reaction. The next one, increase the temperature, what do you do with the reaction rate? Increase the temperature, what happens? Increase the reaction rate. Increase the temperature, increase the reaction rate. Decrease the temperature, decrease the reaction rate. One of the funniest things that occurs this time of year, and right now is not, I say this time of year, in about 2 or 3 weeks, lizards. How many of you have ever picked up a lizard in the fall or early winter? It's easy, isn't it? Why is it easy? They're slow. Why are they slow? They're cold. They're cold. How do lizards get their heat? From the sun or some other source. That's why on those cooler days you will see them sunning themselves on a rock. Because what's that rock doing? Absorbing the heat, and then they absorb the heat. Funniest thing happened the first year I was teaching in Glasgow in the chemistry lab. And this is even funnier. The chemistry lab is on the 2nd floor of the building. This is why, to me, it's even funnier, because it's the 2nd floor of the building. And there was a table, a lab bench up front, and this is probably the first day of lab. And the room was really cold. I mean, they were keeping that building like 69 degrees Fahrenheit. It seemed like it was just so cold in this room. And I was teaching, and I walked down, and I looked down, and there was a blue-tailed lizard. And I just reached down, and I picked it up, and the kids, then I took it around, and of course they were all just like shocked that, one, I could pick up a lizard, one, that I did pick up a lizard, and the fact that there was a lizard in the room. Why could I pick up the lizard? Because it was so cold. Now the funniest thing is, how did it get to the 2nd floor? I just think that's hilarious. I would just, you picture that gecko guy, and he's on his, he's punching the elevator buttons going up. No, it was just, I don't know, but that is so back to this whole thing on, if we had increased the temperature for that little lizard, what would have happened? I couldn't have caught him. I mean, in the summertime, I see these little blue-tailed lizards around my steps all the time. I can't catch them then. But in the fall or in the winter or in a cold air-conditioned room, you can catch them. So it's kind of funny. This affects us the same way. Our body reacts exactly. Now, we're not getting our energy from the sun. Well, we are, but that's another long story. But we don't get it directly like the lizard does. But still, our body reacts to temperature and our reaction rates. And this is where so many times, finally, the students are like, oh, this is a little bit of chemistry that I like, because it's like it relates to your body. And most of you like yourselves. So let's look at this. When body temperature increases, reactions proceed at a faster rate, and you must breathe more rapidly. The heart must pump harder to supply oxygen for the faster processes. When your temperature decreases, reactions slow down, less heat is generated, and then it becomes harder to maintain an adequate body temperature. Now that scenario really should have its own paragraph, and then this sentence be in a separate one. But let's deal with that first part. Have you ever heard of people who fall in really cold water but still are able to be okay after that? And they even, they get hypothermia, but what happened to their body? When they fell in that cold water, what did their body do? Reaction rate wise. what happened to the reaction rates? Did they slow down? Did they slow down? The reaction rates slowed down. So the reaction rates slow down. Now, what happens when you are working out? You get hot. So what's going on? Your reaction rates increase. What do you have to do to supply enough oxygen for all those? You have to breathe harder. Now, something happened to me a few weeks ago that I experienced without me doing anything. And this was something that I had never had happen before. It was a really, really hot Thursday, and it was like one of those 90 to 95 degree Fahrenheit days. And I was bush hogging. I didn't bush hog this weekend, though. But I was bush hogging. Now, the funny thing about our tractor is we have a cab tractor. This is not funny, but it's funny, sort of. We have a cab tractor, but it doesn't have air conditioning. Now, a cab tractor without air conditioning is 100 times worse than a not cab tractor. Because a cab tractor without air conditioning, you don't have hardly any airflow. So you have these awning windows. So you've got these windows here, but you can open them like this. Well, that's just like, imagine here's the window and it's open like that. It doesn't allow much airflow, okay? You've got one door here that opens, and you've got a little door at the bottom that'll open. Well, I have this one tied back. This one I have tied back, and I've already broken it because of tying it back. So now it won't close all the way, and I broke the glass. So now I have this airflow situation a little resolved, but not only do you have the heat of 95 degrees Fahrenheit, but your cab is here, the engine's here, and you're driving this way. A diesel engine gives off a little bit of heat. So what's all the heat doing? Coming back on me. So the great thing is I get a workout by driving the tractor, bush hogging, without me having to do anything. But on that particular day, I overheated just riding in the tractor. And what's interesting is literally I can lose weight. It's like a workout just sitting in the tractor in the sauna, basically. Because what happens, without me even knowing it, what's going on in my body? What am I doing? I'm really sweating. And without me realizing it, I'm breathing harder. And this particular day that I'm referring to, I literally got overheated. I realized when I finally got down, I was in the tractor for like 6 hours. When I finally got down, I'd had plenty to drink, but when I got down, I literally was, my heart rate was pumping. It was like I had gone out and worked out. That was amazing to me, how much this whole scenario affects you with heat. You literally, your body with temperature responds without you even necessarily doing anything. I've experienced it by working out. Yeah, you're pedaling your bicycle, you start to breathe faster, right? But just heating up like that. Now, I've never been a person who's gone to saunas, and I don't know if any of you have, but I would imagine that's the same kind of thing that happens, but I don't think they let you stay in there very long. Am I right? You limit it to 20 minutes, 30 at the max, I would say probably. And that's why. That's why. And so that was a scenario that's kind of interesting to me. Now, throw the next sentence in and let's talk about it in relation to what that paragraph said. A fever is the body's response to increase the rates of defensive reactions that kill bacteria. How many of you know somebody when someone gets a fever, say, of 100 degrees Fahrenheit, or 100 degrees Fahrenheit, 101, oh, you got to give them some Tylenol. Is that a good thing to do? No, it's not. Why? What's the body doing? The body is trying to fight it off. What did my body do in response to getting too hot? Breathed harder, right? Heart rate increased. It was trying to take care of itself. Now, I'm not talking about 105 degree Fahrenheit temperature, okay? I'm talking about a mild fever. What's the purpose of it? It's to solve the problem. It's to solve the problem. And so your body is made so beautifully to fix itself when it can. And that's why you have the fever. That's your body's reaction to that infection, and it's doing its job. So it's kind of an interesting thing. Now let's go the reverse route. Let's go to you have a heart problem and you're going into cardiac surgery. What do you want the room to be, temperature-wise? Cold. Why do you want it cold? You want to be like that lizard. You want to just be, slow me down. I mean, you want to be cold in there. Why do you want to be cold? Because that means your reaction rates are slower. Yes, what are they going to give you while that's going on? Oxygen. Are they going to give you oxygen? Is that going to, by that increase in concentration of oxygen, going to do you see what they're doing? Isn't that interesting how that applies? And that's where we go here. If we increase the oxygen concentration when a patient is having trouble breathing, it will also speed up the reaction rates and get more oxygen into the brain. That's the blood-brain. The blood and the brain. Okay? So it's pretty interesting how this reaction rates, and again, I'm touching like a drop compared to what we could do. The last thing I want to mention is catalyst. Tell me about catalyst. You've heard of this before in some of your other classes. What does a catalyst do? That's right. So it speeds up the rate of reaction. Catalyst speeds up the rate of reaction. A catalyst is unchanged in the reaction and doesn't show up in the product. So a catalyst goes through, is used, but does not actually get used up. What is really amazing, this is something that would be worth your doing just to see it happen. This fall, maybe you're at a campfire. You know that you've got a fast reaction when you burn that marshmallow. So most of you have roasted a marshmallow over a fire, and so you put the marshmallow on your stick and you've got it over the fire, but you know that it doesn't immediately catch on fire. It takes a little time, right? What's that called? It's got to reach the what? Energy of activation. It's got to reach that energy of activation. Now then, once it catches on fire, it goes, right? I mean, it doesn't take long. You can pull it out and try to blow it off, but chances are it's charged, so it's gone. But take something like a nut. Put it in the fire. Does it have a higher activation energy? And then go a step further. Forget the campfire. Now try to do that same little scenario with a match. And you'll start to see how much energy it actually takes and how long it takes for these reactions to occur. Now, why do I pick food items? Because what are you using for your energy? Marshmallows and nuts and other things, right? Do we get the energy from those things fairly quickly in comparison to what it would take in a fire? For some of them we do. Sugar we do. Now yes, it burns fast, that marshmallow does. But there are certain foods, starch is one of them, that as soon as it goes into your mouth, so when I say starch, I'm talking about potatoes, chips, bread. As soon as it goes into your mouth, amylase is an enzyme that you have that immediately starts to break that down and provide you energy. Without catalyst, all the reactions that go on in your body could not proceed fast enough for you to stay alive. That we have to have them. And so they are, and that's the enzymes. And what do enzymes end in? ACE. We'll talk about this more later when we get to this in the biochemistry portion, but enzymes end in ACE, have the ACE ending. All right, that is it for energy. Let's move on to gases. If you watched the video over gases, you are well prepared for today. Couple things I want to point out before we get to the math. Before I even start that though, go ahead and get your calculator out. You need your calculator. Where is the sign-in sheet? Can you send it back down? Just send it back. Has everyone had the sign-in sheet tonight? Can you grab that? Thank you. Thanks. All right, for gas law problems, the temperature must always be in Kelvin. And as a reminder, Kelvin is degrees Celsius plus 273. That's how we get Kelvin, degrees Celsius plus 273. If you don't remember that, you need to add that to your list of things you need to know. You also need to add to your list of conversions that pressure units are atmosphere, millimeter mercury, or torr. And 1 atmosphere is the same as 760 millimeter mercury or 760 torr. Pressure is not something that you guys have dealt with in those units before. Most of you don't realize that you have used those units or ever heard those units. But if you are a weather watcher, and I realize in this classroom there's probably not very many, but a few of you watch the weather. Barometric pressure. Do you know what I'm talking about? You ever heard of that, the barometric pressure? If you've ever watched the weather on the news, they say something about an incoming low pressure front or a high pressure system is going to sit over the... Never heard these phrases before? Some of you have. Thank you. That pressure is what we're talking about here. It's atmospheric pressure. And typically, instead of being in millimeters of mercury, they measure it. If you look at your phone, if you've got a phone that has the weather on it and you look at that and you scroll down and find the pressure, that is in inches of mercury. But it could be converted to this, okay? So you probably have seen that maybe, or at least heard about the pressure before without realizing that that's what you're hearing. Now, where have you dealt with pressure before? Tire pressure. Tire pressure. You've all dealt with tire pressure before if you've ridden in a car, okay, or a bicycle. That pressure has units of PSI, which stands for what? Pounds per square inch. That's what that stands for, is pounds per square inch. You are not responsible for memorizing that one. I will give it to you if you need it, but that is something that would maybe relate to something you know more about with the PSI. All right, each of these is a named law, Boyle's law, Charles' law, Gay-Lussac's law, but you don't have to learn all of those equations. Instead, the only one you were learning is P1V1 over T1 equals P2V2 over T2, which is called the combined gas law. That's the only one you have to memorize. But I do want you to know each of the named laws and their relationship, because I think there's some value. But before I even say this, guys, I want you to realize you already know about gases. You just don't necessarily know you know about gases. Every one of you has gas. I don't care if you tell me you never pass gas. That's baloney. Every one of you has gas. You burp and you pass gas, both ends, okay? Every one of you do this. What do you feel before you pass gas? Whether it's the clean gas coming out of your mouth or the smelly. What do you feel? Pressure. Do you already know about gases and pressure? more than you realize. You just didn't know it had a name, Boyle's, Gay-Lussac's, or Charles. But it does. And so we are going to look at the relationships so that in the real world, you can apply it to what you actually already know. Boyle's law deals with pressure and volume. It's the only one of the named laws that has nothing to do with temperature. It deals with pressure and volume. And as pressure increases, what happens to volume? Volume decreases. As pressure increases, volume decreases. Guys, why are your propane tanks for your gas grills so small? And maybe you think they're big, but they're actually pretty small for what they contain. How can they be so small? What is that gas under? Pressure. It's under pressure. They put it under pressure so that if it's increased pressure, what about the volume? Decreased volume. So the container doesn't have to be so big. Does that make sense? If they didn't put it under so much pressure, the container would have to be bigger. When you open the valve, what does the pressure do? Get released. The volume then does what? What's the gas do? Takes on the volume of its container. Have you ever had a situation where somebody left the gas grill on and it wasn't burning? And you went back out later and you wanted to have grilled something and you had no gas left. Why? What did the volume do? It all escaped. Why? Because the pressure was released. And that's why. Basically, as I said, that's the only one that does not deal with temperature. The rest of these do. So let's look at Charles. Charles' law says as temperature increases, what happens to volume? Volume increases. Gay-Lussac says as temperature increases, pressure increases. Tell me where you know anything about either Charles or Gay-Lussac's law. Tell me a scenario where you've seen this happen. Temperature and pressure or temperature and volume? Increased temperature, increased pressure, increased temperature, increased volume. Where have you seen this happen? Say it.
When it gets cold outside, the tire has the pressure.
That's exactly right. That's exactly right. In a few weeks, some of you will go out to your car in the morning to get in, and maybe the day before it was 75, 80 degrees, and you go out and it had been a cold 35, 40 degree night, and you think, oh my gosh, I got a flat tire, because your whatever indicator says you've got low tire pressure. You do have lower tires. Are they necessarily flat? No. What happened? Temperature decreased, volume decreased, and pressure decreased. Does that make sense? That's what happened. If you really want to kind of get an idea of how this works, and your automobile has the actual pressure, not just low or high indicator or low indicator, but I know my husband's car actually has the actual pressure listed, and I don't know how accurate it is, but it has a number. Go in the morning when you get in your car, look at that number. Drive for half an hour to an hour. Look at the number again. What are you going to see? It's going to be higher. Why? The friction on the road has caused that tire to do what? Increase its temperature, which causes the pressure to increase. Pressure to increase. Propane tanks. What color are propane tanks painted? White or light colors, aren't they? Why don't they paint them? I mean, think about the propane tank if you've got one in your yard. It might look a little better if it were a nice dark green or something where it blend in, right? Why don't they do that? Because that would absorb more heat, which would increase the temperature, which would increase the volume and the pressure. Does that make sense? Okay, so see, you knew all this, you just didn't know it had names. Your body also works with some of these gas law principles. Before I go to the body here, I'm going to deal with this one picture for you. I like how this is listed for Boyle's law. And I think one of the easiest ways to do this is literally with your hands, just imagining. If you have a container of air in your hand, such as this, with a movable piston like that, and if you increase the pressure, what's going to happen to the volume? It's going to decrease. I mean, literally, when you see that happening, that makes sense. So Boyle's law says, here the pressure is 1 atmosphere, here the pressure is 2. So in other words, we've increased the pressure. The volume went from 2 down to 1. So if you double the pressure, you have the volume. Those are questions you may see on your test. Other than just math questions, you may see some concept questions like that, asking you what would happen, okay? So think about the concept of what's going on here. Now, in your body, Boyle's law is actually what causes us to breathe the way we do without thinking about it. And it says that when an individual inhales, the rib cage expands and the diaphragm is lowered, thus increasing the volume of the lungs. According to Boyle's law, if you increase the volume, what happens to the pressure? Increase the volume, what happens to the pressure? Decrease the pressure. Now, what is happening when this occurs is basically a vacuum. You, in essence, have a vacuum occurring, which causes what to come into your lungs? Air. Air gets drawn into the lungs. When an individual exhales, the rib cage contracts. The diaphragm is raised, which does what to the volume? Decreases the volume. Increases the pressure. Yes? Which causes the person to do what? Exhale. Now, try it. Take a deep breath and feel what happens. Take a deep breath. We'll wake some of you up a little bit if you do that, okay? Take a deep breath. What happens? Can you feel it? Now, here's what's kind of goofy but interesting to think about. Try to expand your rib cage without allowing air to come in. You can't do it. Why can't you do it? Because as soon as the rib cage gets expanded, what happens? Air is automatically drawn in. And the same thing is true, okay? So even if you try to hold your breath, what happens as your rib cage starts to contract and your diaphragm goes up? Automatically. You can't control it. Why? Because it's Boyle's law. Somebody might have had an anatomy teacher who did this. A marshmallow inside of a syringe. Did anybody ever have an anatomy teacher that did that? And if you didn't, if you go into anatomy, do you all have a real lab for anatomy? I know, okay, good. I thought you did. Ask them to show you that. See if they will do that. If you have access to a syringe, and I should have brought one and I just didn't do it, take a tiny marshmallow in a fairly large syringe that it'll fit into, put your finger on the end of the syringe or put a cap on it, draw it up, and you will see what basically is going on in your body with the marshmallow. And you'll see the actual contraction and expansion of that. And that's basically the same thing going on here. It's pretty neat. A sponge, I think some people have done it with a sponge too, besides a marshmallow, but the same kind of thing. Where do you see this? Where do you feel, and I'm not going to say this the best way probably, does anybody know a situation in the summertime activities that you do where you feel the effects of your expanded rib cage the most? Swimming, go a step further. Specifically, what in swimming? Diving, you may, that's not where I was thinking. Floating. Have you ever just lied there, floated, and just breathed? What happens when you're just lying there and you breathe? When you breathe in and your rib cage is expanded, what's your body do? Goes up. Then when you breathe out, what do? Go down. Try it sometime. It's really pretty cool. how you feel. You can literally feel yourself going up and down like that. And that's a really good kind of, visual is not the right word, but kinesthetic activity to really realize what your rib cage is doing. And you can actually see that better or feel it better. All right, let's go on to the next two laws in their concepts. And we've got a picture here for Charles' Law. And I say with Charles' Law, think Valentine's Day balloons. I'll explain that in a minute. Let's look at the picture first. It shows us 200 Kelvin and 400 Kelvin. 400 Kelvin is a higher temperature, correct? Guys, cell phones and smartwatches are the same things, in my opinion. I don't want to have to ban them, but stay off of them when you're in class, okay? That's the second person I've seen on a watch. All right, so 200 Kelvin to 400 Kelvin. Tell me what the difference is. Don't say 200 Kelvin. I want to know, what are we doing? 200 Kelvin to 400 Kelvin. Increasing the temperature, doubling the temperature. What's going to happen to the volume? Double the volume. If we double the temperature, it doubles the volume. Doubles the temperature, doubles the volume. And this is Charles' Law. Charles' Law deals with temperature and volume. And then I said, think Valentine's Day balloons. So let's go to Valentine's Day, and perhaps you were in a high school where people gave out those big heart-shaped balloons that said, I love you. You know what I'm talking about? Never got one. I know. All right, so we're bringing up just bad memories here now. All right, so let's just go to the bad memories, all right? Bad high school memories. So the florist comes in, and it takes 10 trips throughout the day, and they bring in this beautiful Mylar heart-shaped balloons, red on one side, silver on the other side, and it says, I love you. And it's just beautiful. And it's full, and it's firm, and it just looks so pretty. I mean, it's just perfect. And they call out the names of who needs to come to the office, and you got called. So you got one of those balloons. And so you were so excited because somebody loves you. The fact that he or she is the ugliest person in class, you just let that go and don't tell anybody. No, I'm just teasing. So then you take your balloon out to your car, and what is the temperature outside in February? Cold. So what does your balloon start to do? It starts to shrivel, and you're like, oh, my balloon has a hole in it. Mama's not going to get to see it. So you stuff it in the back seat anyway and try to hold it down back there. And you get home, and you're kind of all disheartened now because you really got a Walmart balloon instead of the Kroger balloon. So then you go home, and what happens? It magically gets bigger again, and it looks good. And how did that all happen? Charles' Law. You just didn't know Charles had anything to do with that, but he did. Now, something that I tell students to do, and then somebody always asks me, is that his name? No, I say, remember Charles Valentine, but that's not his name. But if you think that, Charles Valentine, then maybe you'll remember volume and temperature, the balloon, volume and temperature. And then you can remember what Charles' Law is, okay? Gay-Lussac's, the memory thing I've got here, and I could have done tire pressure, the same thing. But I put on here pressure cooker, increased pressure, increased temperature. I found out recently that more people than I thought use pressure cookers to cook with. I grew up using a pressure cooker for canning, and we would cook our green beans in the pressure cooker, but I didn't know very many people now use pressure cookers, but it sounds like some people do now. What's the purpose of a pressure cooker? What's the pressure cooker allow you to do? Cook at a lower temperature, give it less energy, but what happens because you put it under pressure? The temperature inside is what? Hotter. Because you increase pressure, you increase temperature. You increase pressure, you increase temperature. Now, even if you don't have a pressure cooker, you have experienced this scenario if you have ever covered up a pot of water that you are trying to boil. When you put the lid on the pot of water that you're trying to boil, that's not an airtight system, but what are you basically doing? Are you increasing the pressure in that pot? Have you ever had someone come along and lift up the lid and you got mad at them? I've had that happen in my house. I have to tell people, don't open the lid. Why do you not open the lid? Because as soon as you open the lid, what are you doing? You're letting all the pressure out, so it's going to take longer. Now, there's a saying that goes along with that. You may know it. A watched pot never boils. That's where that came from.
Back to the balloon thing, is that why balloons, like if you let one float up or accidentally and it is by the light, they pop? Because the temperature.
These lights aren't that much warmer. You're talking about the latex balloons is what you're really talking about usually, the Mylar balloons. I would say it's probably touching something and the skin's so tight is what I would say. Now it could be that it gets hot and you can do that. You can take a balloon, you can take a small balloon that's not as inflated as it could be and put it over something that's hot and it's going to expand. The whole hot balloon process, hot air balloons, it's exactly the same thing. That's why hot air balloons, they start off small, then you keep adding the heat, and what do? They get bigger. And then hot air is less dense than cold air, so that's why they rise.
So you said with the Mylar.
Say that again?
With the Mylar, they'll shrink if it's cold.
The reason you can see the Mylar balloons is because the Mylar is it's not as stretchy as a latex. A latex balloon, you're not going to notice that effect as much. It still happens. You don't see the shriveling. With the Mylar balloon, you've seen this. Some of you have seen what I'm talking about. It's a visual, you can literally see the crinkles in the Mylar balloon because it doesn't have that give that a latex balloon will have. But the latex balloon does the same thing. You could do the experiment with a latex balloon and measure the circumference. You could draw a line around the latex balloon, measure it, take it and put it in a bucket of ice, and you're going to see it smaller. You're going to see it smaller. So it's the same thing. So 3 laws. Go ahead.
Wait, so when a latex balloon shrivels up, is that because it's cooling off, not because there's any holes in it?
No, that is usually when it's got a hole in it over time. Now, can I make a latex balloon shrivel up with cold? Yes. I can take a full-size latex balloon, put it into liquid nitrogen, and it will shrink right up. That's because of a gas law. What you have happen at home after the party is eventually the air comes out.
Okay, because I was thinking maybe if your breath's hot and then
Well, your breath would be warmer and then cool down, but not that much difference. No, not that much difference. That would be a matter of what I'm saying. You could blow up a balloon, draw a line around it, measure the circumference, then take that same balloon, just immediately put it in the freezer, let that air cool down, measure the circumference again, and you're going to find it smaller. That's because of the temperature. Okay? That's because of the temperature. Because you've seen all of these things happen. You've seen all this. You just didn't know it was gas laws. All right, so now then let's do the math. And now how are we going to be doing the math? Here's what I want you to do. What is the actual equation that I've told you to learn? What equation? Did I tell you to learn all of them or just one? What is it? So P1V1 over T1 equals P2V2 over T2. Every time you write that down and then look at what you need and cross out what you don't need. And that way you always have that equation in case you need something of that. What do you not need in this problem? Go ahead, say it again. Temperature. Does temperature make any difference for this problem? None at all. So scratch temperature out. Make sure your units for volume are the same. That would be something you would have to fix if they weren't. And then simply plug it in. So this is V1, this is P1, this is V2, and you're looking for P2. Yes or no? Now, I did put volume before pressure. It doesn't matter. It's still P1, V1. Do you understand the setup? Algebraically, what do you do to get P2 alone? Divide both sides by 5. And if you put units, you will also get the added benefit of seeing that your units cancel and you are left with atmosphere, which is a pressure unit. So 14 times 0.5 divided by 5, what do you get for your answer? 1.4 atmosphere. That is the correct significant figures as well. Do you see that? Question on this problem. Whose law is it? Boyle's law. And I want you to put that so that when you're studying, you start to tell yourself the concept and you look at the question and say to yourself, 14 milliliters at 1/2 of an atmosphere. If I decrease the volume to 5 milliliters, what had to have happened to the pressure? It had to have increased. Did it? Yes. So if you understand the concept, you'll know. The other thing I want to point out at the beginning, I didn't do this today earlier in the class at the beginning, but let me point out something. There is no reason on earth for you to miss these if you understand algebra. Why? What can you do to that answer? Plug it back in. Can you plug that back in? Yes. So as long as you know the equation, you can plug it back in and you'll know every time. Oh, I got that right. Every time. So let's go to the next one. We read through the question. We see that it is a gas law problem. So we go ahead, P1 V1 over T1 equals P2 V2 over T2. This time, what is not important? Pressure is not important, so we scratch it out. There is a typo, lungs, should be the S next to it. What's the volume 1? 1/2 liter. What do we have to do to that temperature 1? Kelvin. So you have to convert it to Kelvin. What do you get? 0.44 liters. That's correct. Mathematically, multiply both sides by 273 K. And you'll see your Kelvin canceled out. And there's your 0.44 liters. Talk to me. Make sense or not? Whose law is this? This is Charles' law. All right, I want you to do the next one. Is Gavin here today? What about Leah Pentacuff? Katie Katrubas? There's a problem with this problem. What is it? Your pressure is in two different units. So you have to change them to the same unit. Does it matter which unit you change them to? No, there's one that's probably easier than the other, and that is 380 millimeter mercury to atmosphere. And if you're mathematically astute, you should immediately see that that is what? Half. 380 is half of 760, so that's 0.5 atmosphere. But again, you could have done it the other way. You could have converted 4 to millimeter mercury. What do you get for volume? 16 liter, and that is the correct significant figures. You need to go back to original numbers to look at significant figures, and that's where the 2 came from. Yes or no? All right, calculate the temperature to which 10 liters of gas at 27 degrees Celsius would have to be heated to change the volume to 12 liters. Again, P1V1 over T1 equals P2V2 over T2. What is not important? Pressure. What do you need to do first? Change 27 degrees Celsius to what? So add 273, and you get 298 Kelvin. Notice some folks are rearranging the equation to start with, and you may do that. That's fine. If you do that, can I not add? I cannot add. I cannot add. It is 300 Kelvin. Sorry, I cannot add. Sorry. Mathematically, this is one of the hardest ones because you're solving for a variable that is on the bottom. And some people simply can't do that. They don't know how. I'm going to let you see what you can do, and then I'll show you a trick if you don't know how to do it. All right, what do you get for your answer? 360 Kelvin is the answer. If you did not get 360 Kelvin, then let me show you a trick on how to solve for a variable that's on the bottom. When you have a variable on the bottom that you try to solve for, the easiest way to do it is flip both sides. So in other words, I'm going to flip this like so. Now, if you've had no trouble answering the rest of these, this one should work too. Multiply both sides by the 12 liters. Liters cancel. Now 12 times 300 divided by 10 is 360 Kelvin. Significant figures. I didn't put the unit on purpose because I want to talk about significant figures. How many significant figures should we have in our final answer? It actually should be 3. It should be 3. Why is it 3? The rule for addition is what? Precision. Number behind the decimal. Here they're precise to the ones. This is 1, so you add that together. Which really, should I have put the 300 with the decimal there and there? Yes. Which means, how do I write this? With a decimal. Does this make sense? If you got it your way, wonderful. You were supposed to be able to get it your way. If you didn't get it your way, then try that flip and it will work. Okay? Before we flip the page, let's go back to, whose law was this? P1 V1 equals P2 V2. Who is this? Boyle's. Who's this? This is Charles. All right, you do the next one. Do the next two. Do the next two. If you're confused on this first problem, there is unnecessary information. What is it? The volume. The volume is not necessary. It's not important. If that confused you, what you could do is use that same volume on each side of the equation. Be pointless. It's going to cancel out if you do that, but you could. You could, but it's not needed. It is not needed. So what is not in this problem? Volume is not in this problem. What do you get for the answer? 1.59 ATM. Mathematically, you multiply both sides by 473 K. Kelvin cancel, and that's what you should get. Yes or no? Whose law? This is a Gay-Lussac. Who's the next law? Tire pressure? Cool garage? Riding the bike? Tell me what about it? Whose law? Nope. Pressure and temperature is Gay-Lussac's. Pressure and temperature is Gay-Lussac's. Does it matter that we're dealing with pressure and PSI for this problem? No, it does not matter. It does not matter. It has to just be the same unit for pressure. And so your answer is going to come out in PSI. Your answer will come out as PSI. Temperature always, absolutely, does not matter. In a gas law, it always has to be in Kelvin. So in this problem, we're not dealing with volume. Is that what you have for your setup? What is your answer? 87 PSI. Again, same thing, 316 multiplied on each side. Kelvin cancel. 87 PSI. Yes or no? Tell me about the next problem. What is it truly? It is the true combined gas law problem. Because look at everything that was there. Are all the variables there? Yes. So it is a true combined gas law problem. Both of these two are. Both of these are true combined gas law problems. So it's going to use everything. P1V1 over T1 equals P2V2 over T2. I'm going to be quiet and let you do it. I want to see what you can do. All right, that should be your beginning setup. Mathematically, we could discuss 10 ways that you were taught to do this. Some people are going to say cross multiply. It all ends up being the same thing, okay? The way I do it is I know the opposite is how to get rid of it. What's being done to it, I do the opposite so that I just end up with P2. So I'm going to take 233 Kelvin and multiply it on each side. That got rid of it here. That gets rid of the Kelvin unit on the left side. That leaves me with 2 liters being multiplied by P2. To get rid of that, I divide. What I do to one side, I do to the other. Liters cancels. Now 750 times 1 times 233 divided by 298 divided by 2. You cannot forget anytime it's on the bottom you divide. So what is your final answer? 293.20 is what you got on your calculator. Let's figure out significant digits. Go back to original numbers. How many? 2. How do I round this? 290 with no decimal, and what am I solving for? Millimeter mercury. Yes or no? Does that make sense? Okay, do the next problem. And the next problem, as far as mathematically, this is the hardest problem you will see mathematically. If you can do this next one, this is like a piece of cake for you. And it should be. You guys were expected to know algebra before you came in. And this is minor algebra. So solve this problem. It is also a true combined gas law problem. Where's the start of your need to pay attention on this problem? Look at volume. What do you see on the units? One is in milliliter and the other is in, so does it matter which one you get it to? No, just make them the same. It doesn't matter. Make sure you get them the same unit though. Pay attention to that.